soil attributes are impacting the decomposition kinetics in various ways, and those are kind of embedded in those equations. But so, for example, you know, in the stuff you guys are going to be working with, you're going to get a soil map, okay? So you're going to get a soil map in a land use map, in a land cover map that shows, okay, I've got sandy soils over here, I've got clay soils over here. And the organic matter and the water balance and the plant productivity, they're going to be different on the sandy soils versus the clay soils. Okay? And there's lots of other attributes of the soils that would really affect, but the texture is a good one to kind of focus in on. You know, you're going to get climate, data, etc. That's kind of how it's going to look. I mean, I think I'm just about, yeah. So let's stop there for a second. Sorry to kind of ramble on too much about the modeling stuff, but wanted to spit it out. Is there any questions then on the, you know, just again the general idea of the, you know, how these models work in terms of representing decomposition processes and soil carbon balance?
You get your K functions just by experimental data?
Yeah, I would say either if a process can be measured potentially, you know, like in a laboratory setting or something like this, you could do a direct measurement of that. In other cases, some of these parameters are determined from model calibrations. So you might have, and for example, lots of this kind of stuff has been done, you know, looking at things like isotope tracers. You know, for example, there's a model very similar to Century that was, it's called the Rothamsted model, Rothamsted UK. And there they had a kind of a unique situation where they have a long-term agricultural experiment that's been going on for about 150 years, actually. They've been growing wheat, and they've been, you know, doing different things like either adding manure or not adding manure, you know, different levels of fertilizer, removing the straw, different kinds of perturbations that would change, you know, something in this carbon balance. So they've got, first of all, 150 years of data of both the input side as well as the changes in soil carbon. So that kind of a situation, you can, you know, you can fit model parameters using that kind of long-term data. Because one of the problems with soil organic matter is that, you know, yeah, you've got you need residence time of 50 years when you need a long experiment to follow that. But the other thing that's, you know, kind of more kind of cool and innovative stuff is things like what's called the bomb carbon effect. So when people were doing atmospheric, I guess it was the U.S. and Russia largely, a little bit of China, but U.S. and Russia back in the 50s were blowing up lots of atomic bombs above ground for at least a few years, and then they put them below ground. But one of the things that happened from that atmospheric weapons testing was you generated a lot of C14, much more than the natural C14 that's created with, you know, ionizing radiation in the upper atmosphere and stuff like this. So there's this big slug of C14. Well, that was like a giant carbon labeling experiment for the gold. And so you could actually, because, you know, basically people know how much C14 and C14 in CO2 is being taken up by plants. So it's like you had a giant labeling experiment. And particularly if you have these long-term experiments, you could say, okay, I know that all of this soil organic matter that I had at Rothamsted prior to 1950, you know, has a normal C14 content. And now all my fresh organic matter after 1950 is, you know, has got this bomb carbon signature. It's enriched in C14 because the plants photosynthesized all that C14O2. And so now you can set up the model to, you know, differentiate between the younger and the older organic matter. So you can both try to simulate the total organic matter changes, but also the changes in the carbon-14 signature as that C14 label kind of propagates itself through the system. So that's, so lots of kinds of, isotope tests, incubations, long-term experiments, that's the sort of thing that go into these.
So in combustion research, there's, when you're trying to model chemical reactions, you have a list of chemical reactions that have constants that are associated with those as well. And so a lot of the research is going back, and it seems like every year someone puts out a new mechanism that has their constants. So how much variability is there among like these constants, and how are the models updated? So like you import your own constant values based on whatever, or is there like a database, like a centralized database, or these things are like, who's the gatekeeper of that?
Yeah, it's a little bit different because you're not dealing with you're typically not dealing with that well-defined system. So you've got this chemical reaction, and therefore you have, these attributes that can be measured under very controlled conditions and where, it's well-defined what you're looking
Well, but that's the thing, you have a certain number of those, but that's maybe like, in some of these big mechanisms, that's like 5 or 10%, and then the rest is based on models.
Yeah. Well, and in that case, there's not a gatekeeper, although there are a relatively few ecosystem carbon models that are sort of in use globally, and there's quite a bit of interaction between those, and there's lots of people that end up doing cross-model comparisons, and they evaluate sort of strengths and weaknesses. But part of it is, the other thing is the models do not uniquely define, there's no general agreement on how organic matter should be divided into different pools. So the Century model says, and most of the models have these kind of, they're called functional, you would say sort of kinetically defined organic matter. They say, okay, I've got 3 pools of non-recognized, so I've got 2 pools of what I'm going to say fresh plant residues. And those you actually probably can define pretty, if you wanted to say these are the plant compounds that go in this box and these are the ones that go in this box, you can do that. And typically they do something kind of like that, use a ligand to nitrogen ratio is what is used as an index of that fraction of the fresh plant material. But in the soil organic matter, the Century model says, well, I'm going to divide that into 3 different pools. I'm going to call one active, slow, and then passive, and the 3 pools. And what actually defines them is essentially that K constant. So the active pool has a mean residence time under ideal conditions of decomposition. So all of those response functions equal to 1 of like 1.5 years. And the slow pool has a mean residence time of, I don't know what it is exactly, but 17 years or something. And then the passive pool has a mean residence time of 350 years. And that's what defines those pools. There's another model, well, I mentioned the Rossi model, and basically if they have a different structure in the organic matter pools, then it's a different model. It's totally different.
So if you want to model, so we're going to be modeling certain counties or certain locations within our respective states, right? So the soil data that we have for that area, that we get for that area, has to match up with the model that we're going to use.
The soil data, you won't be, the model is going to generate the estimates of soil organic matter, and it's also going to, and we'll go into this a little bit probably on Thursday, because one of the issues is with initializing, how much of the carbon do you put in these different pools when you start off your simulation? That's a big deal. But in terms of what you need as an external input, what you really just need is data on the soil physical properties. Okay? So and for this exercise, we're going to make it very simple so that all you need to know is soils are, what their texture is, so if it's sandy, clay, loam, that sort of thing. And the second attribute is something about the drainage status. So were the soils formed under poorly drained conditions versus well-drained conditions? So those two will be good enough for you to characterize, soil differences in terms of the organic matter, dynamics, at least for the purpose of this class. And most of the other stuff you'll need to do is kind of innocuous. So let me finish off, because you'll have ample time to be asking questions about Century and Basin and stuff. Let me talk a little bit about N2O, and then I'm done. So we've looked at soil organic matter, talked about that a lot. The other one that is probably most important for our purposes is nitrous oxide. Okay, it's one of the three major gases, and it also has the highest, per amount of that gas, it has the highest capacity to absorb infrared radiation. That's basically what greenhouse gases do. Methane is another one that's important in agricultural systems, but soils are generally not a source for methane unless they're anaerobic. So flooded, like a rice field, is a big source of methane. But and so to some extent, if you were, we could choose to say, okay, our biofuel crop feedstock is rice straw, and so I want to model rice. If we were going to model rice, we'd have to consider methane as well as an important part of that. But we're not doing rice, and so basically there's not going to be, the feedstock production, methane is not very important. Okay, the carbon cycle is complicated enough, but the nitrogen cycle is even more complicated, and again, for your engineers, there's a chance to really spread your wings. There's a lot of forms of nitrogen in the soil. What's particularly important, I guess, is in contrast to when we talked about soil carbon and organic matter, we focused really on organic organic chemical transformations, okay, carbon in organic forms. There's the organic carbon component of soils is very important, but there's also inorganic carbon that plays a very important role. So this shows kind of nitrogen, how it can go in and out of systems. The main thing I wanted to focus on is really, this guy here, nitrous oxide, and it is a gas that is formed through microbial processes that are involving these inorganic forms of nitrogen, okay? But it's tied to the organic matter cycle as well. And this is how it looks like in a little bit more detail. So all of these are different ionic forms, either as ions or as gases, nitrogen in the soil, okay? And there are two main processes that we care about for this. One is called nitrification, and that's an oxidation of reduced nitrogen towards more oxidized forms. It's done by bacteria, okay? The bacteria are chemoautotrophs, so that means they get their energy from that oxidation. They fix carbon dioxide, not just like plants, but they take out carbon dioxide and use that to build their biomass. So it's an aerobic process, okay? It's just that oxidation. In that aerobic process, there are, N2O is one of a kind of an intermediate process that I guess the best way to describe it is it's kind of a